Is there a pointer? Okay, so good morning, everybody. So today I'm going to discuss how interseismic coupling relate to ruptures during large earthquakes on megathrust. And I will start with recalling the definition of interseismic coupling. Then I will move to discuss two examples, the Sumatra Megathrust and the Japan Megathrust. And in both cases, I will resort to dynamic modeling to see how we can make sense of the observations. So interseismic coupling is defined as the ratio of the deficit of slip, which is accumulating in the interseismic period, to the long-term slip. It's a quantity that can vary with time. And I've drawn, I'm showing a simple cartoon that explains how it relates to geodetic deformation of the upper plate. So in a case where the coupling would be zero, there is no deformation of the upper plate, and in this case, you have a step function in the horizontal velocities across the subduction zone. So now, if the coupling is not zero over a certain width, what you would measure from geodesy is a gradual increase of horizontal velocities. So there is contraction of the upper plate, and the upper plate is dragged down by the subducting plate. And from this observation, the measurement of geodetic strain, you can infer the pattern of coupling along the plate interface. So if in the long term there is no inelastic deformation of the overriding plate, what happens is that the cumulative effect of all the earthquakes must balance the interseismic strain. And so in principle, from measuring the interseismic coupling, you might be able to say something about the probability and the size of earthquake that needs to balance this interseismic coupling. The problem is that there's an infinity of ways of doing that. So the idea is that you're paving the locked portion of the plate interface with a lot of earthquakes so that in the end, they match the long-term slip rate imposed by the convergence between the two plates. And that's a difficult problem. Now, how does interseismic coupling relate to the frictional properties of the megathrust? So the idea is that the friction can be either rate weakening, meaning that the dynamic friction is less than the static friction, or rate strengthening, meaning that the dynamic friction during sliding is higher than the static friction. So when dynamic friction is lower than static friction, you can have a runaway phase, and you can nucleate the earthquakes. And so the idea is that these areas which are locked in the interseismic period have a rate weakening frictional property, whereas those areas which are creeping are rate strengthening. So now in practice, when we invert geodetic data, we don't force the interseismic coupling to be 0 and 1, we leave it free. And so we can end up with a value which is anything between 0 and 1. So for example, if the interseismic coupling is 0.5, then this is the pattern that you would expect across the subduction zone. And in that case, of course, you need fewer earthquakes or smaller earthquakes to balance the interseismic strain. So let's move now to Sumatra. So we have quite a lot of information from geodetic and paleogeodetic studies about interseismic coupling and also the time evolution of slip along that portion of the megathrust over the last few years following the great Sumatra earthquake of 2004. So let's start with the interseismic coupling pattern. So red is a coupling of 1, and 0 is white. So what you see here is that the pattern of coupling along the megathrust is extremely heterogeneous. You see basically two big asperities. And now we're going to see how this pattern of coupling compares with the seismic rupture first that occurred during the Nias earthquake, the 8.6. There's a typo here. I hate seeing my typos projected on such a large screen, I must say. Well, so the rupture during the Nias earthquake coincides quite well with the asperities, the northern asperities. And then following this earthquake, the expectation is that the southern asperities would fail as well. And actually they did, but in quite smaller earthquake than what was expected based on the historical record. So there was first the 8.4 earthquake, the Bengkulu earthquake, which was followed 12 hours later by a smaller earthquake, 7.9. And so what you see is that there's a difference here. The Nias earthquake ruptured entirely the asperity to the north, but in the south, these asperities fell into a complicated sequence. Actually, didn't fail entirely. There's still a big patch that remains to fail. So now, these two earthquakes, the Nias earthquake and the Bengkulu earthquake, produced a lot of post-seismic deformation, which is modeled here in terms of afterslip. And what you see is that there's a complementarity between the coseismic and the afterslip distribution. So afterslip occur both up dip and down dip of those ruptures, releasing a moment of about 30% of the coseismic released moment. And this is happening over a long period of about 1 year. So to sum up what we've seen for Sumatra so far, very heterogeneous pattern of interseismic coupling. The seismic ruptures tend to be confined within the locked asperities. If you look on average from the trench to the down deep end of the seismologic zone, what you find is that about 50% of slip is taken up by a seismic creep. Then you can balance the interseismic coupling with the coseismic strain release over the last few centuries, and what you see is that they match more or less. The misfit is only a factor of two. Okay, there's dancing starting in the background. So what's the conceptual model coming out of this observation is that actually we must have some sort of a patchwork with areas where the megathrust is rate weakening and is locked in the interseismic period on places where it's rate strengthening and it can trip. So where you have a dense packing of rate weakening patches, what you expect is that this will appear as a broad zone of a broad locked zone, whereas where you have asperities which are isolated within creeping patches, they might fail during background seismicity. And so the interseismic coupling will be something between 1 and 0. During earthquakes, large earthquakes, you're going to have several of those asperities rupturing, and the patchwork will be a source of complexity during the rupture. And following the earthquake, there is a stress increase around the rupture, which is going to promote a seismic creep in those areas that are rate strengthening. So some time ago with Yoshi Kaneko and Nadia Lapusta, we've been exploring this concept based on dynamic simulation. So here I'm showing a simulation with two patches which are rate weakening. And we can see that this kind of simulation, this kind of simple setting with only two asperities start to reproduce the kind of observations we've gathered for Sumatra. So you have a movie which is showing here the sliding velocity on the fault. The rate is of a few frames per year during the interseismic period, and it slows down to a few frames per second during seismic ruptures. So what you see is that in the interseismic period, these two patches which are rate weakening are going to be locked. And the locking does not vary much over the interseismic period. It varies a little bit. And then they fail during the earthquake. So sometimes a rupture might rupture only a fraction of one of those patches. And sometimes these two things might rupture together if they are close together. The finding from this study is that there's one quantity that determines both the interseismic coupling and the probability that an earthquake will propagate across that bridge, which is rate strengthening. This is this quantity, which is the product of the width of the bridge by the rate strengthening effect of the bridge. Okay? And that's it. Now, when we look at Sumatra, there's something that we're missing. We're missing the fact that sometimes we do have earthquakes, or tsunami earthquake, in fact, occurring along the trench. And so this happened in 2010 in particular. So this is an earthquake that produced more moment than what you would expect that from the seismic wave radiation. And this area, which ruptured in 2010 during this tsunami earthquake, is close to the area that produced a lot of aftersleep before Bengkulu. So there's one thing that we're missing here, and this is an important thing, because when now we move to Japan, to the Tohoku earthquake, we see that we have a combination here of a regular earthquake at depth, which produced quite a lot of ground shaking, and more like a tsunami earthquake near the trench, which was the cause of the large tsunami. So there's one thing that is missing in this kind of simulations. We have a clue about what happened here from comparing the coseismic and the post-seismic slip following associated to the Tohoku earthquake. So what I'm showing here is the result of the inversion of the geodetic time series from GeoNet, and including also the sea bottom measurements. And what we've done here is a joint inversion of the time series for both the coseismic and the post-seismic. It's important to do that because the sea bottom data cover both the coseismic and several weeks of post-seismic data. I'm showing how the model fits the time series, so it's hard to see, but the pink are showing the data, and the blue is the prediction from the model. And so this is now showing the output of the model. The coseismic is shown in red, and is compared with another model that was derived from the joint inversion of geodetic and seismic data. And here is the post-seismic slip. So you see a nice logarithmic increase of velocity of displacement following the Tohoku earthquake. What is intriguing when you compare these two things is that there's a large overlap of the coseismic on the post-seismic slip distribution, which is near the trench. At depth, it's hard to see. There's quite a lot of afterslip here, but here there is no overlap. There's a clear complementary here of the post-seismic on the coseismic. Up deep, it's very different. They do overlap quite a bit. And this is now an inversion of the interseismic data, again from GeoNet, and including also some sea bottom data that were published by Matsumoto et al. And here I'm showing two end members, so we're following the same approach as Mead and Loveless from some time ago. Here the trench is allowed to creep, and here it's locked. It's not so clear which model is better than the other. The fit to data is a little better here because there is more freedom in the inversion. And then what you can do is combine the model we derive from the post-seismic or coseismic from Tohoku with the interseismic model to describe the cumulative slip along the plate interface as a function of time, and this is what this plot is showing. So we're looking at the cumulative slip over several centuries, so it includes a few historical ruptures, but basically this is the interseismic, so this is the average over the whole area. And then the Tohoku fills the gap, so compensate for the deficit of slip in that area. And then the blue is showing the post-seismic. So the post-seismic does contribute also significantly to balance the interseismic coupling. So whether you take this model or this one, you end up with a different estimate of the written period of the Tohoku-Oki earthquake. It would be around 100 years only with this model, which has strong coupling near the trench, whereas here it's of the order of more like 300 years, which is a little short compared to the historical record. So now, how can we explain that we have this tsunami earthquake and that sometimes a rupture would propagate very close to the trench, while in historical record in Tohoku-Oki earthquake area, actually most of the earthquakes were down deep. One way to solve the problem is to include in the dynamic model the effect of thermal pressurization, and I encourage you to attend the presentation by Nadaya Kuba on this dynamic modeling. The key ingredient is now that we allow for thermal pressurization near the trench, something that has been explored by a recent paper by Noda and Lapusta. And what you see here is that when this is included in the model, most of the earthquakes are going to rupture the area that is right weakening, but once in a while you have a large earthquake propagating near the trench. And it happens only rarely, and this actually would explain the observations that we have for Japan with the overlap of post-seismic and on coseismic rupture. So it's time to conclude, and I'm not going to wrap up the details so that we have time for one or two questions if you wish. Thank you for your attention.
We have time for one quick question, maybe?
Yes. So actually, we've seen this morning presentations, one in particular by Jeff Freimüller, showing that the interseismic coupling can vary with time. And actually, when you do the inversion of the geodetic time series, what you solve for is the accumulative deficit of slip. So if in the time period you do have a slow event, it is taken into account. It is. Yeah. Yeah. Thank you.
Thank you.
That's the last slide.
Our next talk is on controls on upper mantle deformation through the earthquake cycle in subduction zones by Furlong and Hovers, and the speaker is Kevin Furlong.
Great. Well, thank you very much. Following on the theme of today's session, I'm going to be looking at go back some. No. How do we go backwards? There. Okay, thank you. Some modeling and an analysis that Rob and I have been doing, looking at what might control patterns of strain accumulation during the interseismic period and compare that to where strain is being released coseismically and the patterns and timing of those effects. Now, there's simple models that show up in all the textbooks that imply that it's a very simple system. The subducting plate is strong and there's some locked interface and the deformation occurs within the upper plate and we unlock the plate interface and things recover. And as we've seen through talks today, but also over the last decade, the picture that actually occurs in real subduction zones is much more complicated than that. And in fact, there's a whole range of possible deformation patterns that we might see. In an end-member case, you can imagine a situation where the subducting slab is relatively weak compared to the upper plate, and so a lot of the deformation gets preferentially partitioned into the subducting slab. A situation maybe might explain some of the behavior in the Kuril Islands situation, earthquake a few years ago. Or we may have the situation that's more like the textbook view where the slab is relatively strong and most of the deformation is partitioned into the upper plate to be released there coseismically. Or, of course, these are end members and the real world is typically probably somewhere in between. And so what we're going to do is explore what might control these relative patterns of behavior. But this is motivated by a whole sequence of events that have happened over the past decade. Here, just give three examples. In the Solomon Islands case, we had a magnitude 8+ megathrust earthquake. It's an area where there's very young ocean subducting. But one of the interesting things there is that the rupture, there's in fact two different plates subducting in different directions relative to the Solomon Islands. The Australia plate more to the easterly and the Solomon Sea plate more northeasterly. And yet the rupture included fault rupture with both sets of plate pairs, but the slip during rupture, the coseismic slip, actually mimicked the plate motion pre-slip. And so here's a situation where, and there's very little evidence of any relative displacements between the Solomon Sea plate and the Australian plate coseismically in terms of the transform fault separating them did not light up with any aftershocks. And so we see, here's a case where it seems that the upper plate in sort of the textbook view was the dominant player in deformation and strain release. The sort of the other end member we referred to as the Curl events there. We had a sequence of 2 events a couple of months apart. The first was a Megathrust 8.3 on the interface, had 4 to 5 meters of average slip on that interface. And then a couple of months later, there was a major normal faulting event offshore outside the trench. And the total plate lengthening associated with the normal faulting event, once you take into account the geometry, basically mimicked the amount of coseismic slip on the plate interface. And so, there was sort of a net zero if you had a fixed point somewhere out here outboard of the normal faulting event for the slab displacement. So here seems to be a case where some large fraction of the strain accumulated interseismically was within the slab and then was released by this paired set of great earthquakes. And then finally, sort of the clinker in all this are events such as what we saw in Tonga, Samoa a few years ago, in which we had a large normal faulting event outside, again outside the trench, that appears to have triggered a megathrust event that was somewhat smaller. But when we look, for example, at the GPS as recorded in Samoa and American Samoa, we see that the coseismic displacements, irrespective of our reference frame, shows that the displacements here were basically as given by what you'd expect from the normal faulting event. And so it seems that in the normal faulting event, then, these plates move to the northwest, but also that may have loaded the interface and helped drive the event there. So we have a whole range of possible characteristics, and the question is what might be controlling some of that. So essentially what I want to do is investigate 2 different aspects of this deformational style. One is the role of what I'm calling strength, but basically just the relative deformational properties of different parts of the system, the slab, the sort of wedge or forearc, and what I'm calling the margin or the backstop, and how different relative properties of those components may affect patterns of strain accumulation and release, and then also how in space and time the coseismic strain does release and how that compares with strain accumulation. So we've taken a very simple model to look at this. In this early stage, it's an elastic model, simple geometry, so that effects of bending of the slabs and things are not in what we're looking at. And basically, we just, as I said, have 3 parts to the system: a slab, a wedge, and a margin. These could obviously move around in terms of their positions. We have a seismogenic fault, which is locked during the interseismic and unlocked during the coseismic. And then we have the rest of the plate interface, which is unlocked during the interseismic, but will be locked during the coseismic because this is an area that would be normally ductily deforming. So we can just, vary these parameters and see how that affects the patterns of what we observe. And so just as an example of what we can monitor, if everything's got the same elastic properties, the same physical state, we have, after 8 meters of displacement of the subducting plate, you have a pattern of displacements within the system. If before the earthquake, the red curve here is the vertical displacements. The blue are the horizontal displacements. These would be the things that perhaps one could observe through GPS or other geodetic techniques. After the event, we've unlocked coseismically, we unlock the fault, but the rest of the plate interface does not slip coseismically because it's thought to be responding to a different rheological system. But we can then monitor surface displacement, so this would be equivalent of the coseismic we might observe geodetically. And also we can observe what actually happens on the plate interface, what we're calling fault displacement, and those would be things that could be observed seismologically. And so we can then compare all of these things. That's for a very simple case. If we then start thinking about how can things change, well, is there a motivation for that? Well, one of the interesting results that's come out of some of the PBO data that's been collected in the Aleutian system is that there's a change from the area, the eastern Aleutians up into Alaska, where we see ongoing displacements of the upper plate that are compatible with the model of the upper plate deforming. As we get out into the sort of central illusions here, the GPS and the islands that are a little bit further back from the trench, but they show relatively small amounts of interseismic displacements. Now, in a simple model, one might interpret that to mean relatively low coupling along this interface, and that may be part of what's going on. But we do know from historical records that this whole section of the plate boundary has hosted great earthquakes. So this isn't simply an area that does not accumulate a strain or a slip deficit. It does, but it's not apparent in the GPS data that we're looking at. Well, one possibility for that is simply that there is relative rheological differences between the upper plate in the eastern part, where we have continental crust and the continental margin of Alaska, versus the Bering Sea section, where we have oceanic crust in the background and perhaps a stronger backstop to the system. If we have a strong margin, as we have out here in, as we might have in the western section, that tends to concentrate the upper plate deformation near the trench. And of course, that's an area that we have a difficult time observing because it is outboard of the islands, which are the closest to the trench we can put the stations. Whereas if the backstop is comparably in strength to the wedge, which might be the same if this is all continental crust, then we distribute the deformation more broadly, and this is more what you get from having a uniform sort of an elastic model for your strain accumulation, and that is more in concert with what we observe geodetically. So now that's sort of saying some things about what's happening prior to the earthquake, but one of the questions that then comes up is how does this play into what might happen during the earthquakes themselves? And so what we can say is, what is the coseismic deformation in this very simple model? So we can look at what happens to that. How does the coseismic deformation compare to the accumulated deformation that we would expect to be released? And also, how does this propagate across the region? Now, it's important to remember that coseismically, the area that was previously locked is now the free slip area, but this area down dip of that, which was, slowly but at a strain rate comparable to the accumulation rate, was relaxing the deformation, is now, for all practical purposes, locked. It's not necessarily a frictional interface that would obey the standard velocity weakening, velocity strengthening type rules. The other thing we need to remember, though, and this is something that we haven't looked at, but I'll allude to, is that even within the upper plate, we're modeling a simple elastic rheology, but in the real world, this is not an elastic rheology, and so there's going to be strain relaxation within, say, the lower part of the upper plate as it accumulates, and it's only going to be the upper part of this system that will actually host or record the elastic strain accumulation. And so during any elastic strain release up here, that would require we also then load elastically the lower part, which was previously relaxed. It doesn't have built-up strain to be released. So here's just a simple comparison for two different models that are, generally not too different. In this case, we have a strong margin back here, but the slab and the wedge have similar material properties, and so the deformation is partitioned between these two parts of the system. In this case here, the backstop and the slab are equal properties, and the only weak spot is in the wedge area. So, and what we see then in the upper figures, the dashed lines are what would be the slip deficit to be recovered by during the event. In the case of the red is the vertical and the blue is the horizontal in both cases. And then the solid lines are what actually is recovered during our pseudo-earthquakes. And what we see is that, as we've seen very often in the real data sets, the amount that we recover coseismically is only a fraction of what has accumulated since the last major earthquake. In the case of the Tohoku event, it's perhaps a factor of 3 or larger discrepancy between what has accumulated in the last 1,000 years and what was released presently. But we also see that, depending on subtle differences here, that projection. Now, this is important because if we want to use interseismic GPS data to help inform us on what the possible slip deficits and magnitudes of events can be, we have to be aware that we may be misestimating the relative magnitudes. Now, the last thing I just want to point out is that as data sets are improving, we're seeing, we're able to use different types of data and compare them against each other. And this is one of the seismic finite fault models. This is one that Gavin Hayes produced for the Tohoku event. And what we see is that if we do that, and just with a simple sort of Okada source type modeling, and compare that to the observed coseismic GPS data from Japan, we find a very good fit between the predicted by the seismic finite fault model and what is observed. Now, this is not accounting for things like the post-seismic relaxation that we just saw. But we can then, the finite fault model produces a time history of rupture, and we can actually then compare that to a predicted time history of displacement here. But there will be a move out or a propagation rate as this elastic strain release migrates across the region. And although we don't have an answer to that yet, I'll show in a second, this does provide us with some insight perhaps into the mechanisms that allow or help drive the strain release coseismically. So here is just a simple we'll show a model in a second. Here are the data at these three red stations here. The black is the observed data. The red is that predicted by the finite fault model. And the red dashed line would be then the residual, which in a sense would be the transient effect of seismic waves propagating and being recorded by the GPS network. And so just the model as this goes, this is with a lag of 3.5 kilometers per second. As the rupture proceeds, and of course, rupture up here is going to affect stations here, but with a time lag, we are then able to model the effects of the slip. So, in conclusion, just the key points I want to bring up, and this is obviously the start. We're at a stage where we're having data sets that allow us to do things not possible before. I think it's important to recognize that deformational behavior is dependent on the relative strength or material properties of components. The inter- and coseismic displacements should be expected to differ in magnitude and location, but that can be useful, maybe something we can exploit. And the move out of the coseismic deformational response is probably linked to some of the mechanics of how it's being released, and by understanding that, we may be able to say something about the rheological strength of the upper plate. Thank you very much.
Okay, we'll move on to the next talk. Next talk is entitled Coseismic and Interseismic Slip on the Mentawai segment of the Sunda Megathrust during Historic Earthquake Supercycles by Philibosian, C. Avuak, Natawijaja, Chung, Daryono, Suargadi, Shen, Wu, and Hill, and presenting Isbel Philibosian.
Okay, so there's a long list of collaborators that was just mentioned here who I'm working with on this project at the Caltech Tectonics Observatory, Earth Observatory of Singapore, LIPI, and National Taiwan University. So the motivating questions behind this whole session, as well as my project, are we would like to know what is the kinematic history of slip on the fault plane during the various periods that make up the seismic cycle, and how do the various earthquakes and types of aseismic slip contribute to that cycle. Finally, what do these kinematics imply for stress evolution on the fault plane? The Sumatran subduction zone is an excellent natural laboratory to address these questions. First of all, because there are islands located right above the seismogenic part of the subduction zone, which provide a basis for geodetic measurements. We, of course, have modern observations of the great earthquakes which have occurred there recently. And most importantly, the location provides coral as a geodetic tool. Because coral records can be preserved for hundreds or even thousands of years, this provides very detailed data about multiple seismic cycles. Whereas in most subduction zones in the world, those detailed observations would be limited to modern cases, modern earthquakes, which occurred during the instrumental period. So a brief overview of the methods used in coral paleoseismology. These corals grow outward hemispherically under the level of the ocean, and of course they can't survive out of the water. So if a tectonic uplift occurs, we can determine that by seeing that the coral above the water has died. So we can that way measure the tectonic uplift. We can also determine a time series of vertical deformation by taking a radial slice and looking at the growth history of one of these corals. In cross-section, we can see annual bands, which are similar to tree rings. And in the first part of this record, we can see that the coral is growing higher and higher every year, an indication of gradual tectonic subsidence of about 6 millimeters a year. We can then identify and measure a coseismic uplift, another period of subsidence, and then a second uplift. If the uplift completely kills the coral colony, in order to estimate the total coseismic uplift, we have to go and sample a modern coral and look at the interseismic rate. We can make a first-order assumption that this interseismic rate was constant throughout the entire interseismic period within some uncertainty, and use that to determine a best estimate of the coseismic uplift as well as some uncertainty on that. So these are the methods which are employed in the data you'll see going forward. Based on coral records as well as on the modern rupture sequence, the Sunda Megathrust can be divided into these segments, some of which rupture in a single event, such as the 2005 earthquake. But my study focuses on the Mentawai segment, which has a different behavior, characteristically rupturing in multiple earthquakes, in a cascade of ruptures that can be separated by decades. Based on coral records, we can interrogate 4 separate rupture sequences in the Mentawais, and we discovered that each of these has unique characteristics. In the 14th century, we have at least 2 conventional megathrust ruptures, but these were actually preceded by a shallow event. In the 17th century, we actually have evidence for 4 separate earthquakes and some slow slip events interspersed with those. In the historical period, we know the exact dates of 2 conventional megathrust ruptures from historical records, and there may be some aseismic slip as well. And then, of course, in the modern case, we have 4 and at least 1 more future predicted conventional rupture as well as a shallow rupture. So what we can infer from this history is that each of these rupture sequences involves different groupings of each of these asperities, and some asperities may also slip aseismically. We can investigate that diversity of rupture in more detail by looking at the historical rupture sequence. This is an update of earlier work by Mentawai et al. So the relevant data here are the 20th century interseismic rates, the measured coseismic uplifts in 1797, and inferred total coseismic uplifts based on the back projection of these rates. The pattern, somewhat unsurprisingly, as we might expect, has a peak of interseismic subsidence on the west side of the island, suggesting that the fault is coupled down dip of the islands. Looking at the coseismic patterns, you would make a similar inference, and in addition, you can see that the 1797 uplift is tapering and ending to the south, and there's a hint that the 1833 uplift is also tapering to the north. Because the reefs died completely in the northern part of these islands, there is an uncertainty in partitioning the slip between the 2 events, but we can make some educated inferences about what that is likely to look like. and that is that the 1797 event extended all the way up to the segment boundary at the Batu Islands, and the 1833 event terminated farther to the south. To infer what these uplift patterns imply in terms of slip on the fault plane, you can use a fairly simple elastic half-space model. And this is an inversion with a very strong spatial smoothing because, of course, this is a highly under-constrained problem. If you have the 1797 slip can be matched quite well with the slip down dip of the islands. However, the data do not specifically preclude slip in the shallow portion. So these could be considered two end members, which either of which can fit the data equally well. These magnitudes are probably a bit high, so you should ignore those. I meant to take them out. In any case, based on a large tsunami which was reported for this event, it probably has to involve at least some shallow rupture. Likewise, for 1833, it can be matched fairly well with slip down dip of the islands, but again, we cannot preclude the possibility that some shallow slip was also permitted. In comparison to the 2007 earthquake, we can see that there's quite clearly an asperity which did not rupture in 2007, which did rupture in either case in 1833. So this is, again, different asperities being involved in each earthquake depending on the rupture sequence. In addition to a significant variety in the coseismic behavior that we've observed, there are also a diversity in the interseismic behavior. Here is the modern pattern for reference. We can also compare this to the pattern just prior to the 1797 earthquake. And we find that the pattern, in fact, looks quite similar. However, if we then compare this to the data between the two great earthquakes, we find that there are some significant differences. The rates on the central part of the Pagai Islands are fairly comparable. However, both to the north and to the south of those islands, the rates are significantly less, significantly reduced. This suggests that the 1797 earthquake triggered afterslip on asperities both to the north and to the south, and that slip there continued up until the time of the 1833 earthquake. So to conclude, what have we learned from this study? We find that there's a very broad diversity of slip behavior in the Sunda Megathrust. First of all, we have a segment which characteristically ruptures in a series of earthquakes. However, each rupture sequence, the asperities can be grouped variously into the individual earthquakes. We also find that some asperities slip aseismically in each of the rupture sequences. We'd like to, in the future, look at second order variability by doing a full time series analysis of the interseismic rates. And we'd also want to compare the modern behavior after the 2007 event to, for instance, the period between 1797 and 1833, which involves this apparently triggered aseismic slip on certain asperities. We would hope that that sort of comparison may help us anticipate which asperities may rupture in the future events, which are anticipated to balance the slip budget on the complete Mentawai segment. So that's all I have for today. Thank you for your attention, and I'll be happy to take questions.
We have time for a question or two.
So within the coral data, there isn't a... The rates that I showed there are the average over the complete 36 years between the 1797 and the 1833 earthquakes. So these would be a much longer period than, say, the ETS that's in Cascadia. Yes.
Yeah.
Just as a follow-up to that, the A-seismic slip that you see between large earthquakes, can you tell whether that's particularly after slip that is by a big earthquake, or that it's
Well, certainly the case in the dramatic change in the rates before the 1797 event and after certainly suggests that that is a triggered effect. For some of the earlier periods, the analysis is ongoing, and there might actually be slow slip events that precedes the rupture sequence, and in that case it wouldn't be triggered. So it's possible that both types of behavior occur.
Thank you. We'll move on to our next talk, which is entitled, it's an invited talk, The Japan Trench Fast Drilling Project, JFAST, Investigating Large Slip of the 2011 Tohoku-Oki Japan Earthquake with Seafloor Boreholes by Mori, Chester, Iguchi, Tochiko, Brodsky, and Kodaira, and presenting is Jim Mori.
Okay, I'm going to talk about the Japan Trench Fast Drilling Project, JFAST, which was carried out earlier this year. And it's a project mainly to drill boreholes into the fault of the magnitude 9 earthquake that happened off of Japan last year, or in 2011. There's still a lot of observations and analysis going on, so we really don't have that many results to present today, so I'm going to mainly talk about the motivation, the scientific motivation for the project. You all know this earthquake happened. There's lots of slip models from lots of different types of data, but probably one of the main characteristics is the very, very large slip that we see on the fault plane close to the trench. Estimates are on the order of maybe 30 to as much as maybe 70 meters. Really huge amounts of fault displacement happened on the earthquake on the shallow portion of the subduction zone. And of course, as everyone knows, that caused a very large tsunami. The very large slip on the shallow portion of the subduction zone in very deep water is the main cause for the very destructive tsunami that did so much damage on the northeast coast of Japan. So the main motivation or the main objective of this project is to really understand that shallow slip, this huge amount of slip. Seismologists have never really seen 50 meters of slip on a fault before. And so we really want to try to understand that, and I would say it's important because it really is the cause of this huge tsunami. Another point is, we've heard a little bit about this today in previous talks, is there's been some thought that maybe this very shallow region does not slip during big earthquakes, that it's sort of aseismic, or that there's various models that maybe stress is not accumulating on the very shallow portion of the fault, and so you don't get the very large slip. Obviously, this time that was not the case. There was this huge amount of slip on the shallow portion of the fault. Also, as I said, we want to try to understand the tsunamis. It's very important for hazards. And we know that in 2011 there were tsunamis as high as, well, the maximum was 40 meters, but many places with 20 and 30 meter tsunamis along the coast of Iwate prefecture. But in 1896, there was also a magnitude 8 earthquake that had also very large tsunamis, 20, 30 meters. So the only point I want to make here is that you don't need a magnitude 9 to get these huge tsunamis. The important thing for generating the tsunamis is this huge amount of slip on the shallow portion of the fault. And so that's what we're really trying to understand in this project. Okay, so the goal is to understand this great amount of slip. So what can we do? What can we actually look at if we can get to the fault that can help us understand what's going on there? We want to measure the friction during the earthquake. Obviously, friction, it's associated with the strength of the fault. It's associated with the stresses that are built up to the fault. And so we want to try to measure the friction with temperature measurements. And to do that, you have to get there fast, and so that's why we call this JFAST, because we need to make the measurements within about a year or two. We want to look at the stress state on the fault and around the fault. We want to actually try to sample the fault. No one's actually even seen a piece of fault that's moved 50 meters. So almost any kind of sample that we can get of the fault zone is very important. And all this, of course, goes into trying to understand the large slip here. And if we understand there, it's obviously very important in terms of what may happen in other subduction zones like Nankai or Cascadia in terms of the shallow slip, and again in terms of tsunami generation. So the expedition left on April 1st. We were out there for about 2 months, drilling at a site very close to the trench. It was about 200 kilometers east of Sendai. This is the actual site. The target is the plate boundary, which you can see by this very strong seismic reflector. And here it's about 800 meters below the sea surface, the sea bottom. Obviously, we would like to be at a much deeper place, but because of the logistics, this was probably the only place we could actually drill to reach the plate boundary. The trench is here, very close to the trench. It's obviously very complicated and probably lots of different kinds of fault structures, landslides, and so we want to get as far away as possible from this to actually look at the plate boundary. So this is the site that was drilled. Again, it's about 800 meters below the sea floor, and it has a very strong seismic reflection signature in the site data. It's only 800 meters below the sea floor, but it's in almost 7,000 meters of water. And so this was just technically a really very difficult in terms of just drilling the holes. Chicky never had experience of this before, and so we just had a lot of problems getting to the sea floor. And when anything went wrong, it was about a 4-day round trip just to get up and back to the sea floor, had bad weather. And so we had a lot of delays and things that were mainly due to not having experience of drilling in such deep water before. And actually, because of that, we could not install the temperature sensors during the main expedition during April and May. But we were lucky to get some time later on to go back in July, and at that point the temperature string was put into the hole. And so this is the photo of the wellhead at 6903 meters of water depth, and this goes down to the fault zone in terms of the temperature sensors that were put in. As I said, one of the main objectives is to look at the heat signal, to try to look at this frictional heat that was generated at the time of the earthquake. This is the string of sensors that was put in. This is the fault zone, about 50 sensors that were installed in the borehole. And what we want to measure is the residual heat, and lots of times that's expressed in terms of the coefficient of friction. If the coefficient of friction is relatively high, then we would expect to see maybe about 1 to 1.5 degree of temperature anomaly even about 2 years after the earthquake. If it's much lower, maybe around 0.1 or 0.2, then we're down in about a tenth of a degree temperature anomaly. So this is hopefully the kind of signal we'll expect. Right now, all of these instruments are still in the hole, and in February we're going to go back and pull it out and hopefully see something there in terms of the temperature measurements. What can we learn? Well, obviously, just understanding the friction level during the earthquake is very important. I think there's very little constraint right now on what those dynamic friction levels are. If we see a very large signal and we can attribute it to high friction, then we can actually make a pretty simple interpretation that actually stress has been accumulating there over 1,000 years or more. That actually the fault is very, well, relatively strong. stress is accumulating, and therefore the large slip was simply the stress release of this accumulated stress that was going on. If we see a much lower temperature signal, a much lower heat, which is probably, actually we already know that the temperature signal is not huge. We had some measurements during the drilling, and so the temperature is probably, the temperature anomaly is probably, it's less than a few degrees. We have sort of that kind of resolution. So if it is low, there's a lot of more complicated interpretations. For example, maybe stress was not accumulating in the area. We've heard a lot of talk about things like overshoot and ways where you can get a lot of slip that happens even if stress is not accumulating. Essentially, it sort of goes along for the ride, that the large slip at deeper depth can just cause a large slip at the shallow portions. Also, seismologists are always using what we call these slip weakening models for during slip, which means that the friction may be high at the beginning, the static friction, but because of dynamic properties during the actual slip, especially if the slip is so large, the dynamic friction drops. And we hear a lot about thermal pressurization. That's talked a lot about this earthquake. It's talked a lot about, but we actually, up to this point, do not have measurements about permeabilities, fault width, static coefficient of friction, and you need all those parameters in order to evaluate if thermal pressurization is happening. So we hope to get a temperature signal, and we hope to get the associated fault parameters so we can actually evaluate if some of these, or what kind of slip weakening processes may actually be happening on the fault. There's borehole stress breakout information. We see some very nice, clear borehole breakouts in the wall resistivity records. And so these are being used right now to evaluate the direction and even the magnitude of the current stress and the stress change during the earthquake. Coring is also very important. As I said before, we want to actually get a sample. And so we cored from about 648 to 844 meters below sea level. And we're very confident that we actually went through the plate boundary fault zone. And we're confident because we got to the underlying, not exactly basement, certainly not the basalt, but we got to the hard chert, which underlies the overlying sediments of the downgoing plate. And probably the most important sample that was retrieved was this core number 17, JFAST 17. It was retrieved from about 821 to 824 meters. Unfortunately, the recovery was only about 40%, and we only got about 1 meter of material, but we're very confident we got the fault zone. This you can't really see too well, but we got very deformed rocks, very analogous to the type of fault zone material that you see for faults onshore, and this very scaly fabric of a very deformed area. If you put together the amount of material that we did retrieve and did not retrieve, that implies that the plate boundary is less than 5 meters wide. And by plate boundary, I mean the very intense deformed zone where slip is actually happening. So the actual plate boundary between the Pacific and the overlying plate is less than 5 meters. And of course, one of the important analysis that's going on right now is whether we actually have the slip zone of the recent earthquake in that sample. There's some chemical analysis. Looks like a lot of smegtite in that material. And so in summary, main purpose was to look at this huge the huge slip that happened on the fault during the earthquake. Very fast implementation that we could get to the fault within 13 months of the earthquake. Difficult drilling in deep water. One of the most important observations is to try to measure that frictional heat. And so we have temperature sensors in now, which will be retrieved in February. Have good borehole breakouts to look at the faulting. And last, we see we got a very good sample of the actual plate boundary fault zone, and we see a very narrow width of the fault zone, the plate boundary fault zone of less than 5 meters. Thank you.
We have time for one quick question. Wayne.
Let's see. Right, that's a very important part, and that's why we need permeability measurements to see what are the possible flow rates through there. And the other thing, one reason that we want to measure the temperature for about 6 months is the advective and conductive should actually have different time constants. And so we hope to be able to actually distinguish between temperature signals of any kind of flow and friction. So yeah, that's something we hope to actually be able to distinguish in this data.
Okay, thank you.
So the next speaker is Liberty, and the presentation is Megathrust Splay Fault Geometry and Uplift History along the western margin of the subducted Yakutat Terrane, Prince William Sound, Alaska, and it's by Liberty, Finn, Peterson, Hausler, and Pratt. Welcome.
Okay, thank you all. I'm not going to repeat the title again. I'm going to jump right to a slide that's a nice overview that I took from a paper earlier this year from Worthington et al. And what we're looking at is the area here in this red box here, the study area here, which is a transition between subducted Yakutat block here, an oceanic plateau that's being subducted beneath Prince William Sound and central Alaska, transitioning to Pacific plate subduction here beneath North America here. You can see the plate vectors here for Pacific moving roughly north at about 51 millimeters per year, and contrast that here to the Yakutat subduction, which is about 48 millimeters per year, slightly oblique to that here. You can see those red arrows here. See, this is Montague Island here. It has the documented largest slip from the 1964 earthquake. Kodiak Island over here. Anchorage is over here. Let's see, what else do I need to say on this? Leave it at that. Okay, this is a kind of a blow up of that area here. Again, here's Prince William Sound here. Here's the site of the 1964 earthquake here. This region in red here represents the uplift from the 1964 earthquake. These contours represent the top of the Benioff zone. You can see this big deflection here where the Yakutat is being subducted beneath North America here. So you see all the contours of the Benioff zone kind of wrapping around that here. What I'm going to talk about is kind of a compilation of 3 different data sets here that are all focused, again, on this area here. One, we're looking at some bathymetric differencing of data from the 1920s versus data that was collected post-64. We're going to look at a couple of Sparker seismic profiles, high-resolution seismic profiles here, both along the edge of this subducted plate and then outside of the plate here on this purple line here. And lastly, we're going to look at some data from the TACT seismic experiment from the late 1980s, the profile that extends along Montague Strait here offshore and outside of the boundary of that subducted Yakutat slab. A couple of other features on this map worth noting. These contours here represent what's been termed the slope magnetic anomaly, which is a proxy for the subducted southern termination of the Yakutat block here. And here you can see where it's exposed on land and been interpreted beneath the seafloor here. And you can see the continuation of these contours here along this. The idea is that there's underplating of Yakutat rocks here that's causing this high magnetic anomaly. Also, I superimposed the site of maximum plate coupling to the North America plate here from this Zweck model from 2004. Other models using GPS data have shown similar results, but this area here seems to be the area from the GPS data that are recording the largest degree of locking. So just a quick overview of the difference between Yakutat subduction and Pacific plate subduction here along this profile AA prime from this Eberhard-Phillips tomography data set. You can see relatively flat slab subduction. The top of the Benioff zone is dipping at about 3 degrees here along this profile here. As opposed to across the Kodiak Island area here, you can see a much steeper dip to the top of the seismogenic zone here, about an 8-degree dip. And if you use the 8 kilometer per second velocity contour here as a proxy for crustal thickness, you can see right at the transition off of Yakutat onto Pacific plate, you can see a step up of about 15 kilometers here. The area that we're working at here is, again, here's this transition. I didn't put it on here, but this transition here where we've got Yakutat subduction here and Pacific plate subduction here. The circles that you see on this map are uplift values recorded from Plafker's 1969 publication showing uplift from the 1964 earthquake itself. If you look at a profile here, this AA prime, you'll see that the greatest displacement from the 1964 earthquake was along the Patton Bay Fault. Plafker recorded about 7 meters of displacement along this fault right here. And you can see here from this cross section, there were a couple of other players. The Hanning Bay Fault, which is this guy right here, experienced about a 2-meter uplift along the shoreline of Montague Island. And then there was a residual of about 5 meters of uplift here, so we know there's some additional faults offshore to the southeast. Horizontal displacements I also plotted on here. You can see these arrows here. The maximum horizontal displacement that was recorded from the 1964 earthquake was located here just west of this Bainbridge Passage, which is the location of one of our seismic profiles. And you can see the amounts of horizontal displacement are reduced as you move to the as you proceed to the southeast. Across the Patton Bay Fault itself, there was about 12 meters of shortening that was accommodated, or horizontal shortening that was accommodated from that fault alone. So the first thing we did was looked at some data from the 1920s, some bathymetry data, and we differenced it from data from, in this particular area here, from a 1965 survey. And one of the things I didn't point out, and let me go back really quick, you can see this kind of this waffle pattern on the bathymetry here, and that's a result of essentially combining data sets from both before the earthquake, before the 64 earthquake, and after the 64 earthquake. And that was kind of our driver for looking at this bathymetry data in more detail. So let me go to this now. So this is the results of differencing these two data sets. And if you look at, this is the profile I showed from the previous slide on land. If you look at 3 cross sections here where we had dense surveys going kind of east-west, you can see the gold points are from the 1965 survey, the black points are from the 1928 survey. Although we all know GPS wasn't very good in the 1920s, the relatively flat seafloor here allowed us to do some averaging here. And you can clearly see a difference in the topography, or the bathymetry, the depth, both before and after the 64 earthquake. And the nice thing is we've got some differencing data all the way up to the shoreline here, and it's very consistent with the shoreline measurements that Plafker recorded here. So where you see, these numbers are integer values of uplift along the shoreline. Where you see 10 meters of uplift, we're recording from the bathymetry differencing analysis about the same amount of uplift. What you see from this is if you look at this B prime profile, you'll see the Patton Bay Fault, which is this linear feature going offshore here. You're seeing about 6 meters of displacement, compared to the 7 meters on land. And then if you go a little bit farther offshore, you'll see that it's actually 9 meters across this CC prime. You can argue about these little points here, whether they're real or not, that are showing upwards of 12 meters of displacement. But the fact is that there's greater displacements along the Patton Bay Fault offshore of Montague Island here. Now, if you look at another linear feature on the bathymetry here, it projects onshore to what would be called Cape Clear. And Plafker noted in his 1969 paper that there was no displacement along the Cape Clear Fault or across the Cape Clear Fault from the 64 earthquake. But what we're showing here is very little displacement offshore, transitioning to a very large displacement area here. So it looks like the shortening and uplift has been transferred from the Patton Bay Fault here offshore or outboard to a parallel fault system that we've termed the Cape Clear Fault here. And you can see on this DD prime profile, we're seeing upwards of 8 meters of displacement on this fault here. So we're seeing the greatest amount of displacement from the 64 earthquake was in this region here, stepping off outboard to a parallel fault. Another thing to note is the differencing data going all the way up farther to the north. You can see some other linear features here. By the way, the bathymetry is superimposed on this with shading from the north, so you can see all the linear features on the bathymetry. You can see another area that's relatively high here, upwards of 4 meters of uplift, and then you can see it kind of gradually steps or tapers off, and you can see another high up here, which we'll talk about in a minute. I'm going to show you a sparker seismic profile here that goes across this profile right here. These triangles represent the uplift that we've noted. So that's this cross section here extracted from the previous slide, and then this is a seismic profile that we're showing below. Starting from the south, you can see this Cape Clear fault has experienced on the differencing map. So from the '64 earthquake, 7 meters of displacement according to our analysis, and it's on the seafloor. It's a 50-meter scarp. So that's equivalent to given 7 meters per event, that's equivalent to about 7 events right there. And if you move to the north now, the Patton Bay Fault is only showing about 3 meters of displacement along this profile here. And again, on the subsurface, on the bathymetry, we're seeing about 25 meters of displacement on that. So along this profile, the Cape Clear Fault is a much larger player than the Patton Bay Fault. And moving to the north, you can see all these little humps here. This is recording about a 2-meter displacement, another 2-meter displacement, 2 meters, and then 1 meter displacement. They seem to correlate with, here's a nice little bump on what's the along strike projection of the Hanning Bay Fault. You don't see much in the subsurface because the tertiary bedrock appears on the surface or at the seafloor along almost the entire length of the profile, with the exception of areas here where you can see some sediment, and out here you see sediment, and over here. So that's difficult because we can't really do a nice slip analysis on many of these faults along this profile here. This 2-meter scarp here is equivalent to, or along a 80-meter scarp on the seafloor here. This is the offshore projection of Montague Strait. Very rounded appearance. This is a 20-to-1 image here. So you can see this is highly exaggerated. So we've chalked up a lot of this uplift here to either erosion or enhancement from glaciation or multiple recording uplift from multiple glacial cycles. And then you can see another sharp scarp here that's showing about a 45-meter uplift here. We're only documenting about 1 meter of uplift from the 1964 earthquake. So again, this may record uplift prior to the last glacial maximum. Now, these little dots are my pick for the last glacial maxima. We can actually track this reflector offshore to another profile that I'll show you in a minute. And if you look at the uplift from that, it's about 131 meters between what we would call the top of tertiary here and the top of the last glacial maxima. So a little, quick back of the envelope calculation. If you have 7 meters per event, using the '64 earthquake as a proxy for that, 131 meters total from this unconformity, which is a 10 to 13 1,000-year horizon, you'd get about 19 earthquakes, or about 500 to 700 years recurrence interval, which is consistent with paleoseismic measurements in the area that Carver and Plafker have put together. So we think this analysis is pretty solid in this area here. Let's see, we'll move on from there. Yeah, okay, so moving up into the Bainbridge Passage area here, we've got a seismic profile that'll go along here. Before I show that, I wanted to show you another differencing analysis. This is from a 2004 data set subtracted from the 1928 data set. And you can see this Bainbridge fault, which has been mapped on shore as a left-stepping reverse fault here, a thrust fault. And you can see it up here. And if you look at the detailed bathymetry, you can kind of see the outline of the new bathymetry. You can see it as a series of left-stepping and echelon fault segments in this area here that extend offshore. It's been interpreted as a portion of the contact fault system, which was once thought as a terrain boundary, but now is probably just a change in assemblage. But the point here is that the maximum horizontal displacement was recorded here at this site, and you can see the values are diminishing as you go to the southeast. So if you look at the seismic profile here, the point where the Bainbridge Fault crosses the seismic profile here, you can see this inflection point on the seismic data. You can see this almost like a kink band here, where it's relatively flat-lying, steeper dipping, and then flat-lying again here. Unfortunately, we crossed a little bedrock knob just to the north, or this area here, and that likely is not fault related. It's just a knob that kind of sticks out. But you can see pretty clear evidence for some bending, folding, and offsets of these reflectors at the Bainbridge Fault. So the point here is that this is probably the northernmost of the splay faults related to the '64 earthquake, given the fact that there were no horizontal displacements that were greater than what we've recorded here. Okay, so the final seismic profile I'm going to show is what we've termed the junk and trough profile. It's a deep bathymetric low here, kind of a scoured channel here, outside of the boundary of the Yakutat block. So now the Yakutat terrane is kind of moving northward here. So this is outside of that block. And what you see is you see a bunch of little steps on the seafloor here. This is the long strike interpretation of, or the extension of the Bainbridge Fault here. It's about a 4-meter scarp on the seafloor. And you see a number of other steps in here. The biggest one being this Cape Clear Fault. Along this particular profile, we're seeing 39 meters of a difference in the bathymetry between this little bedrock knob and the seafloor down here. But the nice thing about this profile is it seems to have recorded a nice history of the last tens of thousands of years of sediment here. You can see, through the interpretation up there, these dots represent what we would interpret as the last glacial maxima. It's a pretty clear unconformity if you look at this in detail here. But what you also see is, let me take the interpretation off really quick. You can see all these north dipping strata here, and then they're truncated. They're north dipping strata, truncated again, north dipping strata, truncated again. And if you put the faults on there, if you actually stretch, this is about 20 to 1 again. If you stretch this to 1 to 1, you can measure the termination of these reflectors. And you're seeing on this Cape Clear Fault about a 70-degree dip, and then on the Patton Bay Fault, 50 degrees, and all these are around 50 to 55 degrees. And so you see a steeper dip on this splay fault, which would suggest that these faults don't merge at depth, and I'll talk about that in a minute. How are we doing?
30 seconds.
Okay, 30 seconds. So, but what you do see is less displacement. If you look at the offset on the LGM reflector here, you'll see about half the amount of displacement on this profile compared to the previous one, which would suggest that the long-term deformation along this profile is less than what we see on the profile that's along the edge of the Yakutat block. Okay, so I'm going to skip the conclusions there and jump right to one more data set, and that's this crustal scale profile that goes up Montague Strait here. And this is the slope magnetic anomaly, which is a proxy for the edge of the Yakutat block. These were the two seismic profiles I just showed here, and I'm going to show you the seismic profile that goes right along here. And this is from that TAC data set. And what you see is essentially a self-dipping reflector, gently dipping at about 20 kilometers depth. That's the top of the décollement. And what you see are these reflectors that are splaying off of this. This little box here is blown up here. You can see these splay faults surfacing here. And so what we're showing is this is the broker model, the refraction model that was published back in '94. Everywhere where there seems to be a transition from different velocity or a step in the décollement, there seems to be a splay that's surfacing off of that there. So since I'm going to be booted off the stage here in a second, I will leave it at the summary of quickly that the largest displacement that we're seeing in this particular area is right along the edge of the subducted Yakutat block. It seems that the displacement of these faults offshore are diminished. We don't know anything about splay faults along this zone here. We do know that there were tsunami run-ups along this whole area out to Kodiak, so likely these faults continue out into this area here. And these high-angle splay faults that surface here seem to be originating from this 20-kilometer deep décollement at the top of the Benioff zone, and they seem to be related to heterogeneities in the mid-crust. And I'll leave it at that. Thank you.
Well, we don't really have any time for questions, but we'll move right to the next talk, which is an invited talk entitled Slow Slip Events in Guerrero, Mexico, and Consequences on Strain Accumulations Over the Past 15 Years. And presenting is Mathilde Radiguet. The other authors are Cotton, Cavalier, Pathier, Kostoglodov, Vernoy, Campillo, Valpersdorf, Cot, Santiago, y Franco.
So the goal of this talk is to study how slow slip events influence the strain accumulation in the region of Guerrero, Mexico. So the Guerrero subduction zone is located in southern Mexico at the boundary between the subducting cocoa plates and the North American plates. And in this region, there is a seismic gap where no large earthquakes occurred for the last century. Due to the short trench-to-coast distance and the flat slab geometry, the GPS stations, shown in orange, are located just above the subduction interface, and for that reason, this area is well suited to study and record slow slip events. So GPS time series revealed the existence of large transient deformation. So this figure shows an example of the recording for the north component with respect to the fixed North American plate. And we can see the motion toward the north during the interseismic period and episodes of slow slip where the motion is toward the south. So this corresponds to the slow slip events, and the characteristics are the following. So they show large deformation of up to 5 centimeters of surface deformation. Their duration is from 6 months to 1 year. Their recurrence is from 3 to 4 years. And the last 3 events, which occurred in 2001, 2002, 2006, and 2009, 2010, have been well recorded. So the question concerning the occurrence of these events, and particularly in the context of this seismic gap, are the following. So we'll see what are the characteristics of the successive slow slip events in Guerrero. And for this, we'll model and compare the last 3 slow slip events. And in the second time, we will see what are the consequences of the slow slip events on the Guerrero subduction seismic cycle. So here you have the static displacement for the last 3 slow slip events. So the green arrows shows the horizontal displacement. So it's a motion toward the south, and the red bars show the vertical motion. So you can see differences in the extent of the motion. For example, this station who didn't slip in 2006 and show slip in 2001 and 2010. So when we invert the static displacement, we can get an image of the slip distribution on the subduction interface. And here you have the slip distribution for the last 3 slow slip events. So the equivalent moment magnitude is around 7.5. And the maximum slip is between 15 and 20 centimeters. So it's in red here. And you can see that the maximum slip is always located close to the region of the Guerrero gap. So for this event, here and here. So if we have a closer look at a cross-section in this Guerrero gap, what we see is that we have significant slip at depths that are quite shallow, so from 15 centimeters. So this corresponds to a significant slip in the assumed seismogenic zone. And you can also see that the lateral extension is different from one event to the other. So understanding the upper depth limit of slow slip is very important to assess the relation between slow slip and regular earthquakes. That's why, to better constrain the upper depth limit of slow slip, we perform inversion in which we block the slip to 0 in the most shallow segments. So in this figure, you see the misfit as a function of the upper depth limit of the aseismic slip. So on the first dots correspond to slip that is allowed everywhere on the fault. Then we block the slip to 0 on the first line, then on the first 4 lines, etc., up to blocking half the fault plane. So what we see is that for the GPS stations that are located in the Guerrero gap, we see a large increase in the misfit for an upper depth limit of slip of about 15 kilometers. For the GPS stations that are located east of the gap, we see that the increase of misfit is lower. And the same is true for the station located to the west side of the Guerrero gap. We observe the same behavior for the 2002 and 2010 slow slip events. So what does it mean? It means that in order to fit the data of the GPS station located in the Guerrero gap, we need our model to have shallower slip. So the slip seems to be shallower in the Guerrero gap than on both sides of the gap. So where does this come from? If we go back to the GPS displacements, So this figure shows a zoom on the GPS displacement in the Guerrero gap. So the black represents the horizontal displacement and the red the vertical. We can see important lateral variations. So east of the on the west of this blue line, so in the Guerrero gap, we can see that the horizontal displacement are larger compared to on the east side, and particularly on the vertical displacement are also twice as large on the west side compared to the east side. So we observe this behavior for all the slow slip events. So we see that there are important lateral variation in the amplitude of the GPS displacement during each slow slip event. And in order to fit this lateral variation, we need to provide shallower slip in the Guerrero region. So the problem is that the resolution of our model is limited by the configuration of the GPS network, and in particular the fact that the inland stations are located all on the same line. So to improve this resolution, we have access to a stack of 8 interferograms, which cover the period of the 2006 slow slip event. So if we compare the model obtained by inverting GPS data only, so this model I've shown before, if we see how this model fits the INSAR stack, we can see that on this profile here, the model explains fairly well the data. And this first line here corresponds to a region where we have a lot of GPS stations. But on the west side, on the east side, sorry, on this second profile, we see that the GPS model does not explain well the INSAR data. So to improve our model, we perform a joint inversion of GPS and INSAR data. And the result of this joint inversion is a model that can explain fairly well both GPS and INSAR data. So what's the difference between these two models? The new slip distribution here shows a patch here of slip that is deeper than the part, this patch here. So if we look at cross-section, we can see that in the Guerrero gap, we still have the same feature with important slip at shallow depths. And on the east of this Guerrero gap, we have a patch here of deeper slip. So the INSAR data helps constrain the lateral variation in the slip depths. So we've seen that the characteristics of these slow slip events, and in particular the importance of lateral variation in the slip distribution with more shallow slip in the Guerrero gap. And we'll see the influence of these slow slip events on the Guerrero subduction seismic cycle. So for this, we will analyze what's happening on a longer time period and evaluate the slip budget on the subduction interface. So for this, we need to analyze what's happening between slow slip events. So we consider the linear displacement trend during slow slip events. And by inverting this displacement rate, we get an idea of the slip deficit on the subduction interface. And this slip deficit can be interpreted in terms of coupling. So this figure shows the coupling ratio. So it's the inter-slow slip event coupling, so short-term coupling. So a coupling of 1 means that the area is fully locked, and a coupling of 0 that it's slipping freely. If we look at a cross-section in the Guerrero gap, we see that the shallower segment is not coupled. Then we have a high coupling region, and the coupling is decreasing toward the north. So this gives an idea of the short-term coupling between slow slip events. And then we can consider what's happening on a longer time period. So we consider 12 years corresponding to around 3 cycles of slow slip events. So in this 12 years period, we can evaluate from this coupling model, we can evaluate the slip deficit for these 12 years. And we can also consider the cumulative slip corresponding to the 3 slow slip events. When we add these two terms, we get an idea of the long-term coupling of the subduction interface. So by long-term here, I mean only the 12 years that we have considered. So this is the image of the slip deficit for 12 years. And what do we see? So we see that in the Guerrero Gap region here, we have a slip deficit of about 10 centimeters for 12 years, whereas on both sides of the gap, we have a larger slip deficit of about 40 centimeters for the same time period. So we really see important along strike variation in the slip deficit. And this slip deficit model explains fairly well the GPS time series that we have here. And in particular, we can see, so the dotted lines represent the prediction from this slip deficit model. So it explains well the trend. And we see that for the two stations in the Guerrero Gap, you see that the north displacement toward the north is less important than for stations that are located on both sides, which means that we have less strain accumulation for this station compared to the adjacent stations. So we can now compare this slip deficit model with the location of earthquakes and slow slip events. So in blue, you see the contours of large earthquakes that occurred in the last century. And what we see is that the region of high slip deficit coincide very well with the location of large earthquakes over the last century. And the location of slow slip events somehow fills the gap, especially in this region. So this figure shows that the region with high slip deficit coincide very well with the areas of recent large earthquakes. So some conclusions. So we've seen that slow slip events in Guerrero are characterized by an equivalent moment magnitude around 7.5 and important lateral variation in the depth of slip, with slip that is more shallow in the Guerrero seismic gap compared to adjacent regions. We've also seen that there are lateral variation in the strain accumulation in the Guerrero region, with the strain accumulation in the gap that is only 1/4 of the accumulation on both sides of the gap. And regions with high slip deficit coincide well with areas of recent large earthquakes. And this means that there's probably an increased recurrence time of large earthquake in the Guerrero seismic gap. Thank you.
So we have time for 1 or 2 quick questions.
So the question was about the geometry. How well do you know the geometry of the subduction interface? Because we assume that the slip occurs on the interface. So we tested this. There have been some seismic imaging of the interface, so it's rather well known. But still, we tested this by performing different inversion with different geometries, and we've seen that it doesn't change our results.
I also have a question. So what is your constraint on the slip very close to the trench? Is it well constrained or?
Well, the fact is that there is no station very close, but compared to other regions, the distance between the trench and the coast is very small. So I would say it's only 60 kilometers from the trench to the coast. So even the GPS stations that are located on the coast can rather well constrain this slip.
Thank you. If there are no further questions, we keep on with the next talk, which is Sorry, the lights are so bright we can see. Okay, there is one more question. Go ahead. Sorry.
I'm sorry, I didn't get the question.
Non-volcanic tremor.
Oh, yeah, so the non-volcanic tremor in this region, they are locating north of they are not located on the same region as the slow slip, but they are locating further north. So it seems that the northern limit of the slow slip is where we observe tremors.
Okay, thank you again. So now we'll continue with the next talk, which is imaging transient slip events in southwest Japan using reanalyzed Japanese GeoNet GPS time series. And the presentation is by Liu and with co-authors Moore and Owen. Welcome.
I'd like to switch gear to the slow slip events in southwestern Japan using the reanalyzed Japanese GeoNet GPS time series. My co-author Angela Mori, Susan Owen process all the GPS data used in these studies. So Japan has a large earthquake happened frequently due to the subduction of Pacific plate and the Philippine plate beneath the Japan island. So one of most recent example is Tohoku earthquake in northeastern Japan. In southwestern Japan, we also have two historical large earthquake happened in the past. Two most recent events is the Tonankai and the Nankai earthquake. This showing the coseismic slip distributions. And over the past, we have been using the 10 years GPS data processed at JPL from 1996 to 2006, look at plate coupling in southwestern Japan and also in the Tokai area. We also look at the transient slip from 2000 to 2004 and look at the spatial temporal relationship between transient slip versus the strong coupling as well as a low frequency earthquake. And what we found is that there's a complementary spatial pattern between strong coupling area, transient slip, as well as a low frequency earthquake. And recently we have reprocessed GPS data using the improved GPS orbits and covering the entire GeoNets over the much longer time span from 1996 to 2012. And those reanalyzed GPS time series provides a foundation for us to look at other slow slip events, also compare the one we have studied, and re-examine those spatial temporal correlation between transient slip, plate coupling, and also other silent earthquake. So in this talk, I'm going to first talk about reanalysis of GPS time series covering the 16 years time span. Then I'm going to show you the time-dependent slip inversion results for 2009, 2011 Bongo Channel slow slip events. And based on the improved GPS time series, we can also revisit the old slow slip events from 1996 to 1998, and we compare with the one we have studied, 2000 to 2004. And based on the systematic study of slow slip events in the Bongo Channel region, we look at the relationship between recurrent slow slip events, slip deficit accumulation, low frequency earthquake, and discuss the implication for slip transient generations. So GPS analysis, we have been processed all the GeoNet GPS data, which has about 1,400 stations covering the 16 years time span. And the processing done is using the GPS network processor, which is based on Gypsy-OSIS precise point positioning processing strategy. And it's done in the distributed processing on the Linux cluster. For the GPS reanalysis, the three major improvements we have used is using the improved estimate of GPS final orbits. And also we use the global mapping function as well as single receiver phase ambiguity resolution. And once we have a raw time series, we did further GPS time series analysis using the COCA And this analysis mainly helps us to estimate the common mode error and remove that common mode error across the entire GeoNet network. So the time series analysis basically involves identifying the offsets, doing some weighted least square fitting, including all the major components in the time series. Then we subtract those model components based on the residual time series estimate using the pretty simple component analysis, and then remove the common mode errors, then re-estimate the model components. It's just showing the one example using the station near the Bongo channel area and showing the data and also the model. The model actually fit very well. So once we have clean GPS time series, we did the transient sleep modeling in space and time using the modified network inversion filter, which is a common filter-based inversion approach by incurring a priori positivity and spatial smoothness constraints. And we have improved the method to try to incorporate the complex fault geometry so that we can adopt the realistic determined fault geometry, subduction geometry from seismic studies. So this is just showing the simple comparison between reanalyzed GPS time series from JPL versus Japan GSI processed GPS time solution on the left part. And we also compare with the 16-year time GPS versus the old time series solution we have used before. And as you can see, the JPL solution and GSI solution, they agree generally very well with GSI, although GSI looks like have much more outliers compared with the JPL solution. We also find that the reprocessed GPS solution have a much better consistency over the 6-year time span and also reduced the scattering compared to the old time series, especially in the early days where we don't have very good control on the GPS orbit informations. So I should mention that those kind of improved GPS solution in the early days really help us to look at the early days slow sleep events and identify the more detailed sleep evolutions. So we applied the time-dependent inversion method to the most recent Bongo channel slow sleep event, 2009-2011. This just showing the surface displacement by calculating the project position versus actual data, and the actual displacement showing roughly in the southwestern direction, in opposite direction of plate convergence, indicate that slow sleep events actually acting to relieve the strain accumulated on the plate interface. So I'm going to show one sleep rate movie, demonstrate how that sleep rate evolves with the time. Also, I'm going to show you that low frequency earthquake how that related affects the adjacent low frequency earthquake appearance. So the red dots low frequency earthquake, initially it's appearing in a relative kind of background mode. Roughly in the September of 2009, the slow sleep events start to initiate to the northeastern corner of Bongo channel, roughly this area. Once initiated, it quickly migrate both southwestward and updip. And roughly in the middle of 2010, it's shift to another sub-event in the southwestern corner. In the same time, there's a smaller events to the northeast part. And as you can see, if we see this movie again, there's also stronger correspondence between increase of the sleep rate versus the increase of low frequency earthquake once the sleep initiate. Notice that nearly all the low frequency earthquake is located in the down-tip edge of the strong sleep area. You can see the low frequency earthquake really concentrate on the down-tip areas. So indicates that the slow sleep events actually driving the occurrence of those low frequency earthquake. So we put some cumulative sleep versus low frequency earthquake. You basically have a strong sleep, low frequency earthquake locates the down-tip edge, and there's a detailed sleep rate at the selected fault patch versus low frequency earthquake. You can see there's a clear correspondence. Interesting thing we found is that it looks like a Tohoku earthquake basically interrupts the normal course of this slow sleep events. And as you can see, that actually sleep rate is not goes to completely to the back to the zero level, and as also showing those kind of accumulated sleep distributions. HAROS has been found that in addition to the triggering effects of the down deep edge of low frequency earthquake, that's also triggering of very low frequency earthquake in the up deep area, showing that's near Nankai Trough area. And what he proposed is that there's a potential slow sleep event extend further up deep, driving this part. And I think alternative interpretation is that this area may be in a state is very sensitive to the small stress perturbations, and the long-term sleep transient actually imposes stress perturbation over this part, and the triggering the very low frequency in this part. Actually, the recent study by Katama and Safar showing that this area does have very high pore fluid pressure and very low stress, seems consistent to this stress triggering hypothesis. So this just showing the model at the selected GPS sites, the black dots showing the GPS, and the red curve showing the model. The model and GPS fit very well. And we also apply this similar method to revisit 1996 to 1998 Bongocello slow sleep events. One striking feature is that first one, we see clearly the trend sleep for the 1996, 1998, they locate roughly the same location with a similar spatial correlation with the low frequency earthquake. But we also see clear the post-seismic sleep following the Hakunada earthquake happening in the 1996. And if you look at sleep transient, sleep trend evolution history, it appears to that Hakunada post-seismic sleep doesn't propagate in the central of trend sleep area. It's always bounded in the southwest corners. And if you combine these two together, you get the moment magnitude about 7.1. If you only concentrate this part, concentrate the trend sleep part, you have 6.9. I should mention that the sleep evolution for this event is also similar. It's actually quite simple. Is that if you have sleep initiating in the northeastern corner, basically migrate southwestward. So we can basically compare these two slow sleep events versus what we found. They have a similar spatial pattern. We also found that this one is also consistent with what we found. There's a strong temporal correspondence between slow sleep events versus low frequency earthquake. And actually, the sleep evolution details is actually different from this 2000 to 2004 events, is that we have actually smaller events initially in southwestern corner. And once these smaller events goes away, we have new events starting from the northeastern corner and expand southwestward. So if we put them together, we get those kind of pictures. So 1996, we have relatively simple evolution history, northeast, southwestward. And for the 2002 and 2009, you have quite different evolution details. But one dominant feature is all similar across the three events. All the major sub-events initiate in the northeastern corner and migrate southwestward. So given that all the events initiate same location on the plate interface, we think it's controlled by some inherent frictional properties on the plate interface. But the details in terms of sleep evolution and also their difference imply that they also subject some secondary factors like local stress perturbation or pore fluid pressure variations. So we can put them together, try to get the sleep budget based on those recurrent sleep events. Also, the detailed version of the sleep history give us better capability to look at the recurrent intervals. We basically get the sleep events between those three events, recurrent interval at 4.6 years, and all three events locate in the down deep transition zone, actually part of overlap of a strong coupling area. And we can estimate sleep deficits versus actual sleep rate released by those slow sleep events. They're basically showing this table, showing that the slow sleep events relieves most of the accumulated sleep deficits over these down deep transition zones. So what that imply for the fault zone property and slow slip event mechanisms. First one, seismic study has demonstrated one is essential constitute for the slow slipping generation is the high power fluid pressure. Also, based on the rate and state friction, depth-dependent rate and state friction, Liu and Rice showing that the slow slip events can generate spontaneously at the down deep transition zones. But given that all the slip events initiate roughly at the same location on the plate interface and migrate in the similar fashions, that indicate in addition to the depth-dependent frictional parameter as well as the high power fluid pressure, we also should consider the lateral heterogeneity of frictional parameters on the plate interface. And also, since the transit slip actually actively relieve the accumulated strain on the plate interface, we think we cannot use the tremor as a proxy to help define the down deep limits of strong coupling in southwestern Japan. So the main conclusion is that we found that the 2000 most recent Bongo Channel slow slip events has a very complex slip history, and it appears to be terminated prematurely by Tohoku earthquake. And all three events initiated roughly at the same location, and also integrate the plate boundary, and slow slip events confirm the deformation of the spatial pattern we've seen before. Recurrent slow slip events does trigger adjacent slow slip low frequency earthquake, but still not clear how that stress perturbation affect large earthquake generation in the up deep seismogenic zones. Thank you.
Thank you. We have time for one very quick question. Okay. Is there anyone there? No, not this time. Okay, so we're for the last talk of this session, it's an invited talk, contrasting behavior between shallow and intermediate depth earthquakes. It will be presented by Germán Prieto, and co-authors are Flores, Berosa, and Barrett.
Okay, thank you very much for staying. I know you are all hungry, but this is going to be short. So I want to talk about some of the observations that we can get from shallow events and how they compare to deeper events. We call it intermediate depth events. In this particular case, coming from the Bucaramanga nest shown in northern South America in the figure. This is the typical figure we show to our students, our undergrads, when we teach geophysics. We have earthquakes mostly related to tectonic plate boundaries, although that's not always the case, but most of them are. And we show them, okay, we can, with the depths, we can see the subduction zone, the Benioff zones. But the question that they might have is the physics behind the rupture of these events different when you go to depth? And what I'm going to show you today is looking at macroscopic parameters of the seismological observables of these deeper events and compare them to what we see for the shallower events. And some of the parameters, we call them static. That means seismic moment, corner frequency, the dimension of the source, stress drops, and other parameters related to them. And some of them are more dynamic, related to the radiation of seismic energy. The ones in bold are the ones I'm going to talk about today. And when we start answering this question, we can look at this figure and its temperature against depth. And what we see is that at depths below 50 kilometers or so, you wouldn't expect brittle failure to occur, but rather other kinds of displacements, ductile displacement, ductile flow, instead of fracture. So the mechanism of intermediate depth earthquakes and deep earthquakes is not yet well constrained, but still they represent a significant amount of our earthquake catalogs. So this is the data we're going to be looking at, although we're going to be looking at more data, but this is the more specific one. On the top left-hand side, we have the San Jacinto fault zone and a magnitude 5.1 earthquake and some of the aftershocks. I'm going to show you some results of that. On the right-hand side, we have magnitude 3s to 5s Northridge aftershocks from Mori, Abercrombie, and Kanamori. And on the left bottom part, we have intermediate depth earthquakes from the Bucaramanga nest. So I'm going to try to compare some of these parameters that I talked about for all these data sets. And in order to look at the source parameters, we have to look at the seismic data, correct for attenuation, side effect, and anything that happens between the source and the receiver to be able to observe or try to determine some of the source parameters. So I'm going to use 3 methods, and all of these methods together get us a result that seems to be more stable than just using one. On the figure, I'm showing you the spectral estimates after attenuation correction for this Bucaramanga earthquakes located at 150 kilometers depth approximately. We're talking about 250 events, although I'm showing just 4 examples. The red lines represent the data that has good signal-to-noise ratio. The green part of the spectrum we're not using for fitting these source parameters. And I'm showing you both S and P waves spectra. P-wave spectra. And you see that the signals are pretty nice, actually, for these deep events. We can also use what we call the spectral ratio method, where we sort of divide the magnitude 5.2 there by the spectrum of the magnitude 4 event, and we can try to estimate the source parameters, the relative seismic moment between the 2 events and their corner frequencies. And here's an example of that. On the left-hand side, the P waves and the S waves of the spectral ratio, the fit, that's using a Boone spectral model. And on the top, you can see the corner frequency of the larger event. It's going to be always the larger event as the main shock, and the empirical Green's function is shown in the corner frequency of the empirical Green's function is shown in blue. And you can see that as sort of expected, the larger events have smaller corner frequencies, meaning that the size of the rupture area is probably slightly larger. And we can also do this, the source time function estimation. Now, this is also quite simple. It's simply to take this spectral ratio and FFT back into time. Now you have to keep the phase, but which we actually do, and we get the source time function. Because these last two methods use an empirical Green's function, we don't have to know exactly the attenuation or the side effects, and we can still get a pretty decent estimate of the source spectral source time function. So on the left-hand side, I'm showing you the answer, the earthquake in the San Jacinto fault zone, with 4 examples of source time functions. And on the right-hand side, I'm showing you a magnitude 5.2 Bucaramanga earthquake. And the main observation there is that obviously the signals on the right-hand side show a very small short source time function compared to the left-hand side, even though the events are similar in size. Now, this here is showing you some of the source parameters that we use to describe the earthquake source. This is taken from Allman et al. We have seismic moment, the size of the earthquake on the x-axis, and the corner frequency, the point where the spectra starts to drop down. That's called, we call this corner frequency, and this is for mostly shallow events at different places in the world. When we add the Bucaramanga earthquakes, I'm going to go back and forth, we can see that most of the majority of the estimates of corner frequency for the Bucaramanga tend to be on the high end of the corner frequency plot. So that suggests higher stress stops. We can also look at the source dimension. Now here we have to assume a particular model. We assume a circular fault. And on the left-hand side, I have a compilation of mostly shallow events from Viegas et al. And on the right-hand side, I have the results from Mori et al. In the Northridge area. And when we plot the source dimensions for the Bucra-Manganese earthquakes, we can see again, I'm going to go back and forth. Again, we see that for similar sized earthquakes, say at 10 to the 15, the source dimension is much smaller for intermediate depth earthquakes. Another way to look at compare two events is to not compare their parameters, which could be biased, but look at the actual source spectrum once attenuation and other side effects have been corrected for. The plot shows the log relative amplitude versus the frequency for the magnitude 5.1 earthquake in the San Jacinto fault zone. That's shown in black and with the error bars in gray, the gray area. And on the other line, the red line, represents the source spectrum of the largest Bucra-Manganese earthquake in our data set. And you can see an actual, very consistent difference there. The point of the break of the spectrum, when the spectrum starts to deep down, is much higher in frequency than for the Bucra-Manganese earthquake than for the shallower event. That suggests then that the source of the deep event is much more constrained. And in principle, you would expect that the energy radiated by this event is going to be higher, but it turns out that because of the depth and the density and the velocity, the wave speeds at those depths, the actual radiation of energy is not going to be as high as you would expect. And I'm going to show you the results in a minute. So this is radiated energy for shallow events in the Northridge area and other Southern California larger events. This is data taken from Mori et al. These are shallower events, and again, we can estimate the radiated energy for the Bucra-Manganese earthquakes. And as you see here, radiated energy is slightly smaller for the deeper events than for the shallower events. So when we put these two pieces of information together, the source dimension or the source dimensions, the stress drops, and this lower or close to lower radiated energies, we start to see some important parameter that we call seismic radiation efficiency, not seismic efficiency, radiation efficiency. When we plot that, here's the radiation efficiency, how much energy that was available during rupture is released as seismic waves compared to what's used somewhere else. For the Bucra-Manganese earthquakes, which are the diamonds there, they tend to be consistently lower than the same estimate for the Northridge events. You can see that in Northridge, there's no scaling, no apparent scaling. For the Bucra-Manganese, the scaling is also not apparent, but it's definitely true that the radiation efficiency for the deeper events is much higher, much lower than for the shallower events. So this is telling us something about the dynamics of the rupture, how energy is distributed during rupture, and why or how deeper events or intermediate depth events are, in fact, somehow different to the shallower events. So, in conclusion, we have, from estimates from other studies, stress drops for shallow events that are around 3 megapascals, while for the deeper events we're talking about 30 megapascals, and in some cases for particular events we can get up to 500, 300 megapascals. That, even just by comparing the source time functions, remember a plot where I showed the source time function for two different events, one deep, one shallow. The source time functions, the duration of the rupture is much smaller for the deeper events. The size of the rupture area is expected to be much smaller than a similar size earthquake at shallower depths. We get lower radiated energies, even though we have a very concentrated rupture area with a large slip to account for the seismic moment. The radiated energy is not as high, and that's one of the reasons we don't get really large ground motions for deeper events. On top of that, they are deeper. So that means we have lower seismic efficiencies for deeper events compared to their shallower counterparts. And the interesting thing about this study is that we have done a careful review of at least 280 intermediate depth earthquakes. The advantage of this area is that all the events are concentrated in a single place, so we can perform constant Q analysis, we can do empirical Green's function, we can even get source time functions for the larger events. And from those, we can estimate some of the source parameters. And what we get is that we have these very low seismic efficiencies, and this has also been observed for deep earthquakes, but mostly for larger deep earthquakes, magnitude 6 and above. What we're seeing here is a collection of events, medium-sized events, 3.5 to 5.2 events at intermediate depth that also show lower seismic efficiencies than their shallower counterparts. So these results will hopefully help us in defining what the physical mechanism for intermediate depth earthquakes is. Will it be dehydration embeddlement? Will it be thermal shear runaway? Whatever the mechanism is, has to be able to explain this low seismic efficiencies, high stress swaps that we see for this data. Thank you very much.
Well, we have time for questions. Are there any?
The shallower events, the collection of data is much more widespread. So we have information from, but for the, there were some examples from outside California. There are some studies that show, for example, different behavior or slightly different behavior for Eastern U.S. events. That's definitely the case. They tend to have higher stress up, but they also tend to have higher radiated seismic energies, while these deeper events seem to have higher stress up, but lower seismic radiated energies, lower efficiencies. Now, it is true that the Bucaramanganese is a particular place in the world. I think it's the first best data set available for starting this kind of studies, because we can get rid of information about attenuation and side effects that we can't at other places in the world.
Thank you. Well, that concludes the session. Thank you all for staying. And I'd like to draw your attention to the accompanying poster session that will be in the afternoon. Posters around 2,600, 2,700. I hope to see you there.